For the effect of the catalyst on the rate of reaction, we have drawn the graph between the potential energy and the reaction coordinates. Figure 1 shows the graph for a normal reaction, while the figure 2 shows the graph shown by the black color in presence of the catalyst. If we see the figure 1, here A represents the reactant, which on receiving a energy that is called the activation energy forms the complex, that is the activated complex, which is unstable intermediate, and get disintegrate and forms the product P. In figure B, we have drawn two graphs. Blue color shows the reactant or reaction path without the catalyst, and black color shows the reaction path with the catalyst. So it is providing the alternate path for the reaction, and the required energy for the forming the intermediate complex is EA dash in presence of the catalyst. So it is the activation energy in presence of catalyst. Let's take some problems. First question is, the addition of a catalyst during a chemical reaction alters which of the following quantities? I have discussed earlier that addition of the catalyst changes the activation energy, so option B is the correct option. Second question is, how enzymes increases the rate of reaction? By lowering the activation energy, by increasing the activation energy, by changing equilibrium constant, or by forming the enzyme substrate complex. We know that enzymes are the catalyst, and in presence of catalyst, the rate of the reaction is increased by lowering the activation energy. So option A is the correct option. Third question is, by the action of enzymes, enzyme is a catalyst. So in presence of catalyst, the rate of the biochemical reaction will increase. So option B is the correct option. Fourth question is, the temperature dependence of rate constant K of a chemical reaction is written in terms of the Arrhenius equation, which is K equal to A into e raised to power minus EA by RT. EA is the activation energy of the reaction and can be calculated by plotting. We have already done it, taking the log on both sides. So log K equal to log A minus EA by RT. This implies that log K, that is equal to minus EA by R into 1 by T plus ln A. So this equation is similar to the equation of the straight line, that is y equal to mx plus c, where minus EA by R act as the slope of the line and log A act as the intercept on the y-axis. So we can draw the graph. This is the 1 by T on x-axis and ln K on y-axis. Intercept is ln A and slope of the line is minus EA by R. So using the graph between the log K and 1 by T, we can calculate the activation energy using the slope. So option C is the correct option. Next question is, the rate constant K1 and K2 for two different reactions are 10 to the power 16 into e raised to the power minus 2000 by T and 10 to the power 15 into e raised to the power minus 1000 by T respectively. The temperature at which the rate constants are equal is, we are given that K1 equal to K2 and K1 is 10 to the power 16 into e raised to the power minus 2000 by T and K2 is 10 to the power 15 into e raised to the power minus 1000 by T. So we can write 10 to the power 16 by 10 to the power 15 is equal to e raised to the power minus 1000 by T divided by e raised to the power minus 2000 by T. So it will be equal to 10 and it is equal to e raised to the power minus 1000 by T plus 2000 by T. So we will have 10 equal to e raised to the power 1000 by T. Taking the log on both sides, it will be ln 10, that is equal to 1000 by T ln of E. Because base is also E, so this ln E has the value 1. Therefore, ln 10 will be equal to 1000 by T, and the temperature T will be equal to 1000 by ln 10. We can write it is 1000 by 2.303 log 10, which is with base 10. And so this value will be 1. Therefore, temperature will be 1000 by 2.303. Hence, option B is the correct option. Next question is, activation energy of a chemical reaction can be determined by, and the option A is the correct option, that is evaluating the rate constant at two different temperatures. From the Arrhenius equation, we have already derived that log K2 by K1, it is equal to EA divided by 2.303 R, where R is the gas constant, into T2 minus T1. This is the difference of the temperature divided by T2 into T1. Next question is, for a reaction, activation energy EA is 0 and the rate constant at 200 Kelvin is 1.6 into 10 power 6 per second. The rate constant at 400 Kelvin will be. From the Arrhenius equation, we know that log K2 by K1 is the ratio of the rate constants at two temperature T1 and T2. It is equal to EA, activation energy, divided by 2.303 R into T2 minus T1 by T2 into T1. It is given that activation energy is 0. So log, which is base 10, K2 by K1 will be 0. Or we can write K2 by K1 equal to 10 raised to the power 0, and it will be 1. Hence, K2 will be equal to K1, that is equal to 1.6 into 10 power 6 per second. Hence, option B is the correct option. Next question is, an increase in the concentration of the reactant. Concentration refers the number of the particles in per unit volume. It leads to the change in the, so if concentration increase, then the collision frequency will increase. So option D is the correct option. Collision frequency is defined as the number of collisions per second per unit volume of the reaction mixture, and it is represented by Z. So rate of reaction in terms of collision frequency is defined as P, this is the probability factor or steric factor, into ZAB, this is the collision frequency between the particle or molecules A and B, into e power minus EA by RT. This e raised to power minus EA by RT refers the fraction of the molecule which has the energy greater than or equal to the activation energy.